All right, today we are diving into something truly amazing. We're going to be decoding nature's melody, exploring how scientists are using artificial intelligence to literally listen to the sounds of our planet. They're turning everything from the rustle of leaves to the songs of birds into a powerful way to check on our environment's health. Let's get into it.
So let me just start with this question. What if we could take the pulse of an entire ecosystem? I mean, really understand its health, its stress levels, its diversity, but not with our eyes, with our ears. This isn't some far-off science fiction idea. It's the real question driving a whole new field of science. And honestly, the answer could completely change how we protect our planet.
So to really get why we need to listen, we first have to wrap our heads around the problem we're facing. And it's a big one, a silent crisis. We're losing biodiversity at a shocking rate, and frankly, our old ways of keeping track just can't keep up anymore. You see, birds, they're kind of like the canaries in the coal mine for our planet. Their presence, their variety, it tells us so much about the health of a place. But the old school ways of monitoring them, people with binoculars doing manual surveys, it's incredibly hard work. You just can't have a person in every single corner of the Amazon, right? These methods are expensive, they can disturb the very animals we're trying to study, and they just don't work on the massive scale we need. It's pretty clear we need a better, smarter way to do this.
And that better way? Well, it all starts with putting ears on the planet. This brings us to a technology called Passive Acoustic Monitoring, or PAM for short. This is the foundation for everything else we're about to talk about. So think of PAM like a global network of microphones. Scientists can put these small, pretty cheap devices all over the place, in remote rainforests, across the Arctic tundra, you name it. And they just sit there and listen, 24/7, capturing everything. It doesn't disturb the wildlife, it can scale up massively, and it creates this absolutely colossal amount of data about what's really happening out there.
And what these devices are capturing is called a soundscape. Now, this isn't just a bunch of random noise. It's this rich, complex tapestry of audio that holds vital clues about an ecosystem. It's basically the complete acoustic fingerprint of a place. But to make sense of it, we have to understand what it's made of.
So every soundscape has three main parts. First, you've got Biophony. These are the sounds of life. Bird songs, crickets chirping, all the animal calls. This is usually what scientists are most interested in. Then there's Geophony, which is the sound of the earth itself. Wind whipping through trees, rain, a flowing river. And finally, you have Anthropophony, which, you guessed it, is the sound of us. Machines, traffic, human chatter. By pulling these three layers apart, we can start to build a really clear picture.
Okay, so we have this absolute mountain of audio data. How in the world do we sort through it all? Well, that's where the Codebreakers come in. This is the job for machine learning, which gives us two main tools for digging through these incredibly complex soundscapes.
Now, to make this really easy to understand, let's think of it like this. You've got the detective and you've got the pollster. The detective is super meticulous. They're listening for one very specific clue, like the unique song of a single endangered bird. The pollster, on the other hand, has a totally different job. They're listening to the entire crowd. They don't care about one specific voice. They want to get a sense of the whole room, the overall diversity and energy. Is the crowd big and vibrant, or is it small and quiet?
So the official name for our detective is Soundscape Component Recognition, or SCR, and its whole game is precision. We train AI models to sift through countless hours of recordings just to pick out the specific voice of one target species. This gives us incredibly detailed data, like exactly when and where a certain bird was hanging out. And our pollster? Well, that method uses something called acoustic indices, or AIs. Now, instead of trying to identify individual species, these AIs use math to measure the properties of the soundscape itself, like how complex it is or how evenly sound is spread across different frequencies. The idea is that a more complex, buzzing soundscape probably means there's more life, more biodiversity. It's a fast, big picture kind of approach.
And believe me, the scientific community is paying attention. Just look at this chart. It shows the number of research papers published on both of these methods over the last 5 years. You can see this huge surge in both, especially for the more targeted detective approach. This tells you that scientists see massive potential here, and the race is definitely on to make these tools even better.
But of course, it's not that simple. Nothing this revolutionary ever is. Listening to nature is, well, it's messy. There are some really big challenges that scientists are working hard to solve, and knowing what they are is key to seeing the whole picture. Get this, one of the coolest and most difficult problems is that, just like people, birds have regional dialects.
An AI trained on a finch's accent from one forest might totally fail to recognize a finch just 100 miles away because it sings a little differently. That's a huge hurdle when you're trying to build AI models that work everywhere.
And both of our codebreakers have their own set of challenges. For the detective, the biggest headache is just getting enough data. You need thousands of labeled examples of a bird's call to train a good model, and that's hard to come by. Plus, you've got all that background noise and those tricky dialects. For the Pollster, the problem is more about correlation. A high score on an acoustic index doesn't always mean high biodiversity. It could just be a really windy day. Figuring out which index to use is still a bit of an art.
So, with all these challenges, you might be wondering where this field goes from here. Well, the future is incredibly exciting, and it's all about making these tools smarter, tougher, and more connected.
So what's on the horizon? First, getting everybody on the same page, standardizing how data is collected so we can compare a study from Brazil to one from Borneo. The next huge step is using multimodal AI models that don't just understand audio, but also satellite images and text data for a location. We also just need better theories to really lock in the connection between sound and biodiversity. And maybe the most important thing, combining the two approaches, using the Pollster for a quick wide-angle look, and then sending in the detective to zoom in on the important stuff. And all of this work, all this complex science and incredible data, it's all pushing toward one single powerful goal: to transform conservation from slow, manual work into an intelligent, data-driven, and real-time operation that can help us protect species before it's too late. The planet has a voice. The symphony it plays is filled with data, telling the story of its health, its struggles, its resilience. For the first time in history, we're building translators, powered by AI, that can finally help us understand this ancient language. The planet is speaking. The only question left is, are we finally building the tools to listen? Thanks for tuning in.